And these are the partners. We have partners in the area of lignocellulose and nanoparticles manufacturers. We have partners in the production of the PHB, the processing area, then the co-extrusion and co-injection molding, and end users, in this case, it's Fermas and Arcelic. And these are the data of the project. We had 15 partners from 9 countries, 9 SMEs, 2 large companies, and 4 RTOs. We started in July 2010, and the project will last for 4 years. The budget is $4.5 million, and the funding is 3.4 million. You have the website also for further information. The next project is a project focused on packaging, film for packaging. It's an active multi-layer packaging based on optimized PLA formulations for minimally processed vegetables and fruits. And the idea here is to increase the shelf life of fresh vegetables through specially tailor-made packaging based on PLA. One of the problems we need to overcome is the limitation in flexibility of the PLA, and also we will include in this material some antimicrobial functionalities. Of course, always taking into account safety and nutritional concepts. The material will be fully degradable in composting conditions. We will use encapsulation techniques for the antimicrobial additives in order to avoid them to degrade during the processing phases of the packaging production. So the objectives: improve PLA flexibility, improve water barrier properties, and the processability with the adding of different additives. To achieve the best cost-benefit ratio and optimal performance of the products, we will use co-extrusion techniques. And the new package will provide protection against environmental agents and will improve quality, shelf life, microbiological safety, and nutritional values. And the product will degrade according to the standard. Here you have the organization of the project. We will work in all the areas we mentioned before. We have 10 partners from 5 countries. 6 of them are small and medium companies. We have a large company as end user and 3 research organizations. And the general information, we also started less than 1 year ago. This is a 3 years project. Normally, this is a project target for SMEs. The normal duration is 2 years in these projects, but as we need the biodegradation test, we ask for an extra 1 year more in order to be able to make the development of the material and then to run all the degradation tests. The project budget is $1.5 million and the funding is $1.1 million. HYDRUS project. Here the idea is to obtain pipes. This type of pipes, here you have. This is a result of the project. Basically, this is for micro-irrigation pipes. And one of the main problems we have with this application is that after the harvest, they need to collect these pipes. The material, actually is done by polyethylene, is extremely degraded, and it's not useful for recycling, for example. So we have a lot of waste, and the agricultures need to do something with it. So in this case, it looks very simple, you see, it's a pipe. But the application is extremely demanding because you have, at least in Spain, we could reach very high temperatures in soil. You have all the chemical products affecting this material at high temperatures, and you have the UV radiation, and all this together makes the polyethylene the best material for the application. And to use polyethylene from natural sources will not solve the waste management problem. So we decided to organize a project where the final product could be biodegradable, fully biodegradable. The real goal could be to degrade these pipes in soil. We are at a certain level of the project where we know that this is possible, but with a previous treatment that it's extremely aggressive to the material and, of course, to the soil. So we agree with the farmers and the European Commission that as the material will degrade exactly in the same conditions and time as the vegetable waste. When you have the harvest, you have useful things and vegetable waste. So it's better to take all together and to send it to the composting facilities. In this way, the pipes will degrade exactly in the same conditions, and we will have no waste at the end. So that was the general explanation. If we go for the objectives, so this is the application. Can you see? So you use this, and the drips that are injected parts where the water flows. So we are developing material for the extrusion process, for the pipes, and for the injection for the drips. The full title is Development of Cross-Linked Flexible Bio-Based and Biodegradable Pipes and Drips for Micro-Irrigation Applications. This is also a project for research of the benefits of SMEs in the program capacities. We also have here 3 years project because of the biodegradation test. The total budget is around 1.5 million and the funding 1.1 million. And we finish the second year. We already have, I think, as you can see, the pipes and the drips, and we are making the trials in farms, in real trials in the field. These are the partners of the project. So the objectives were to develop plastic pipes and drips for micro-irrigation produced with biopolymers that could maintain their functional properties during the lifespan and biodegrade after use, to solve the most important problem related to the use of micro-irrigation pipes, that the removal and the disposal. But the problems are we need to fulfill with a biodegradable polymer the mechanical requirements to be processable by traditional plastic processing methods. The plastic processors are not, do not like to change the way they work. To be harmless after the biodegradation, to be thermally resistant, to be chemically resistant, to be recyclable and economically viable. Not recyclable after use, but the scrap material. And be environmentally friendly, achieving a positive life cycle analysis. Our goal was to produce a material with at least 75% on bio-based content. 100% biodegradable, but 75% at least in bio-based content. And to understand the structural changes, including the cross-link and change branch reactions in the biopolymer blend. To overcome the lack of technical knowledge that exists about the pipe extrusion process in combination with reactive extrusion, and to design rules and limitations of this innovation in order to know where we can move, and to modify the thermal and chemical resistance and the mechanical properties. The problem we have here is that we need good elasticity, but not too much, but we need an excellent recovery of the material. This is the structure of the plan. So we obtain two compounds, one for extrusion, one for injection molding. We reach the 75% of bio-based content, and both materials had been processed with no problems. We used normal machinery. And we tested the mechanical, chemical, internal pressure, and biodegradability. So this is the project. And here you have the data. The baseline materials are the bio-based polymers we use because this is not a new polymer. This is a commercial polymer that we modify in the compounding and extrusion process. So the base materials we use are the raw material 1 and 2, and those are the properties we have. The target data is the polyethylene material used nowadays for pipes. The results in work package 2, you can see we improved a lot some of the properties, but not too much others. But in the work package 3, when we went not to the laboratory machines, but to pilot plant machines, we even overpass the mechanical properties we need in both materials. So with these materials, with these properties, we produced the pipes and we went to trials in field.